Chalo. So you got let's do a simple one. Cl2 reacting with KBr. Would they be a reaction or will they not be a reaction? So I got Cl2 reacting with KBr. So the first step was you write down the reactants, right? What are your reactants? Remember to treat the so remember that you're supposed to I mean Cl2 is a molecule, so don't break it up into ions. KBr is an ionic compound, so it's K+1 and Br -1. The next step was you write down all the electrode reactions, whichever ones that are given. So we're going to do that. So you got Cl2 reacting 2 electrons and in equilibrium with 2Cl-1. So I'm just doing this with memory. So this one is already given in the data booklet for Cl2. So write all electrode reactions which involve any one of these. These are your reactants, and let me open the data booklet as well for this one. Okay, I already have one open. So Cl2 K+1, K is over here. We've got K over here. That's minus 2.92. So we're going to add that. So it's K+1. And it's +1 electron, and it's in equilibrium with K. And this one, the E naught is minus 2.71 volts. And then you have a third one, which is bromine Br -1. So you're going to look for Br -1 wherever you see Br -1. Probably in B over here. This is Br -1. So I'm going to write this electrode. It's 1.07 volts. So that is Br2 plus 2 electrons in equilibrium with 2 Br -1. And the E naught is 1.07 volts. So we have these three reactions. These are the only electrode reactions that we have. And we need to figure out, next step is, once you have written down all the electrode reactions or just marked them in a table that's already given to you, all you have to figure out is who has the highest potential. It's the first one. That is the one that's going to gain electrons. So that's our higher E naught. But just a second, let me leave a message. So this one, that's your high E naught. And I told you that you have to ensure that it's your reactant that is gaining electrons. So it is Cl2. We do have Cl2 as one of our reactants. So it's got to be one of our reactants. And then I'm going to figure out who loses electrons. The one that has the lowest E naught is the one that's going to lose electrons. This is the lowest E naught. That means it's the one that's going to lose electrons. But I don't have K with me. I don't have K anywhere. I do have K+1 ions, but I've got no K. So I'm not going to actually use this equation because there is no K present. So we're gonna cut this equation. We're gonna cut this equation out. And then by default, the lowest one is going to be this one. That's going to be our lowest E naught. That's the one that's going to lose electrons. And do we have Br -1? We do have Br -1 as one of our reactants because it's given over here. That's Br -1. So you've been able to figure out who's going to lose electrons, who's going to gain electrons. This is the one that's going to gain electrons, and this is the one that's going to lose electrons. Make sure that the number of electrons gained and lost are equal, which I think they already are equal. This is 2 electrons, and this is 2 electrons lost. So they're already equal, so no need to multiply any equation with anything. Just add up the reactants, and you add up the products, and you'll get your overall equation. So the reactants, the first one is Cl2. And in the second one, the reactant is 2Br minus 1. And the products are, in the first one, the product is 2Cl minus 1. So that's your product over here. And in the second one, the product is Br2. So that's Br2 over here. And you've finally been able to figure out what your overall reaction is going to happen when you react. So we've been able to figure out our overall reaction when you have these things reacting. So we've been able to figure out Cl2 with KBr. This is the reaction that's going to happen. And how vigorous this reaction is going to be, we can figure out the E0 cell as well, which is going to be the reduction potential minus oxidation potential, or higher minus lower. So it's going to be 1.36 volts minus what, 1.07 volts. So what do we get? I think it's 0.29. So it's going to be 0.29 volts. That's what we are going to get in this reaction. Is this clear? Alicia, is this clear? Zoha, Nadine, is this clear?
Yes, sir.
I said now moving to a slightly, so we'll do more questions in past papers, but this is what you're going to be doing. Moving to a slightly and just a quick recap, like if what we did yesterday, right? The steps are, where did we write the steps? Steps are write down the ions, whatever the reactants are, write down all the electrode reactions, every possible electrode reactions, because we don't know at the moment what's going to happen. Like out of these, who's going to gain, lose electrons, and then pick the higher E naught and the lower E naught. But you have to make sure that it's one of your reactants that is gaining or losing electrons. If it's not your reactants, just remove that equation. Don't use that equation. And then you, at the end of the day, write the overall reaction or calculate the E naught cell. So you're going to do the same thing, but now we're going to move towards a slightly more difficult thing, which is that sometimes what happens is that you have chain reactions. Like a chain reaction is like a reaction. When it happens in 2-3 steps. I mean, the chain reaction is not the technical term. I just made that term up. So I'm just going to call it a chain reaction. So first thing is, I'm going to warn you about chain reactions. Chain reactions are specifically for substances that are getting oxidized or reduced in a number of steps. For example, look at cobalt over here. You don't find any equation for cobalt going directly to cobalt 3+. So what would happen is there's going to be a reaction first, and cobalt will first get oxidized to cobalt 2+, then that cobalt 2+ will get oxidized to cobalt 3+. So that's how it's going to go down. So you have to look out for chain reactions where the same element has multiple equations. Look at chromium. There is no equation for chromium going directly to chromium. I mean, there's actually one. So you do have one. So over here, you can have that in one step, but for copper there is available. But look at manganese over here. Manganese has many equations. It's Mn going to Mn2+, then Mn2+ going to Mn3+, then it's Mn2+ turning into Mn4+, which is MnO2. Then it's I think this is this is +7 Mn going to +6. This is +7 Mn going to +4. This is +7 going to +2. So Mn has so many equations. So Mn can have multiple reactions, one after the other. So you have to watch out for chain reactions, especially for substances that have many equations, like vanadium over here going to 2+, then vanadium 2+ goes to vanadium 3+, then vanadium 3+ goes to, I think, not really sure what this is. I think this is +6. It's going to be minus. This is +4, and so on. So vanadium has many equations. So I'll explain this by doing a question first, and you'll get what the idea is. So remember, watch out for chain reactions. Especially applies to elements that have many. So it especially applies to elements or substances that have many oxidation states. So probably, I mean, you don't have to worry about chlorine because it's going to be Cl2 or Cl-1, so that's easy. So here's one. Let's say I want to figure out a reaction between tin and iodine. So it's a simple reaction, like just two substances. No issues over here. So you've got two reactants. It's SN or I2. So I'm going to write down all electrode reactions involving SN and I2. So I'll just copy from here. So SN, there's only one equation where I see SN in. This is this. So I'll just try and copy this one. So that's my SN equation. And the other one is I2. So let's go and find I2. There's only probably going to be just one. So that's just one. And that's 0.54. So let's just. So I've got just two simple equations. And I want to figure out who's going to gain electrons, who's going to lose electrons. So just a second. So here are my two equations. Higher potential gains, lower potential loses. So this is the higher potential, it's going to gain, and the lower potential is the one that's going to lose electrons. That's it. And are my reactants present? So tin is the one that's losing electrons, so I do have tin. And who's gaining electrons? It's iodine, so I do have iodine. So both equations are perfect. No issues there. The electrons are already balanced, so all you have to do is add up the reactants. So it's going to be in the first one, the reactant is the first one, the reactant is SN. And in the second one, the reactant is I2. And you add up the products. And in the first one, the product is SN2+. And the second one, the product is 2I-1. And let me add a word over here. Let's say iodine is in excess. So let me add this. The question states that iodine is added in excess. It would still be the same if it wasn't added in excess, but this is the reaction that's going to happen. So that's my redox reaction. And it's got this positive E0 value, so that's also fine. So there's nothing wrong with this. But here's an issue now. And that is, this is the first reaction. This is reaction number 1. And this reaction has already taken place. Now, once this reaction is over, what do you have in your container? Your container contains, your beaker contains your products, which are tin 2+, and it's 2I-1, so it contains these ions. And it also contains the iodine, which has been added in excess. So it contains the iodine that's added in excess as well. So it contains all of this. So what I'm going to do is, I'm going to watch out for another reaction. Would there be another reaction that's going to happen if these things are present? So remember, tin 2+ and 2I-1 are produced, and the iodine is in excess. So I'm going to repeat the whole process now. So my reactants are tin 2+, I've got iodine, and I've got I-1 as well. So I'm going to first write down all electrode reactions that involve tin 2+. So is this idea clear that once the first reaction has happened, we are now trying to figure out, would there be another secondary reaction after the first reaction has happened? And I've shown you a picture of what the beaker would look like after the first reaction has already taken place. Is this point clear? Alicia and Nazdeen Zoha, is this clear?
Yes, sir.
Chale, so we're now going to try and figure out I mean all possible reactions for tin 2 plus. So tin 2 plus, where's tin 2 plus? So I've got these two reactions involving tin 2 plus. So I'm going to copy both of them. So that's one. And what's the other one? It's iodine. It's the same one. So I'll just go and copy I2 and I minus 1. It's the same reaction. There's only one electrode reaction involving iodine. So this one has also been copied. And I'm just going to so here are the three reactions. So who gains electrons? The higher potential is the one that's going to gain electrons. So it's going to be iodine. That's the one that's going to gain electrons. It's the higher E naught. And I do have iodine. Remember, it was excess iodine that was added. So I do have, there is iodine remaining from the first reaction. So I do have iodine, so it's going to gain electrons. And the lowest one is going to lose electrons. So the lowest at the moment is this one. And it's the one that's going to lose electrons. But remember, you don't have tin anymore. Originally, you did have tin. I mean, initially you did have tin. But now, once the reaction has taken place, the first one, all the tin got converted to tin 2 plus. So your beaker now contains tin 2 plus. So tin is no longer there. So this reaction needs to be removed from the set of reactions because so I'm gonna just cut this reaction out. I'm not going to use this because I no longer have tin. So the lowest one is this one, 0.15. So that makes perfect sense. It's going to be, so this one is our lowest one. And I do have tin 2 plus. So that's a perfect reaction. So I do have tin 2 plus in my beaker. So I'm going to write down the overall reaction now, add up the reactants and the products. In the first one, sorry, in the bottom one, iodine is the product. Sorry, the reactant. In the top one, the reactant is tin 2 plus. And then you have your products. The products in the bottom one is 2i minus 1. And in the top one, it's tin 4 plus. So that's your product. And the E naught cell is also positive. So you have another reaction. So what's going on is, so here's your second reaction now. Okay, that's reaction number 2. So just quickly summing this up, what happened over here? You had your first reaction initially, that tin and iodine reacted, and you figure out that tin is the one that's going to get oxidized, iodine is the one that's going to gain electrons. And you did that, and the tin got converted to tin 2 plus, you had 2i minus 1, and there was excess iodine that was left over. Then you figure out, will they react again? Then you started doing the whole process again. You wrote down all the electrode reactions involving tin 2 plus and I2 and I minus 1. And you figured out that iodine is the higher potential, so it's going to gain electrons again. And the lowest potential was the first one, but you cut that out because the tin has gotten used up, so there's no tin left. So the lowest one was this one, the tin 2 plus 1. That's the one that's going to lose electrons, and you got your two reactions. So is this clear? This thing? So this is known as a chain reaction. It's like once the first reaction happens, then you have another reaction. So I'm going to write down the overall reaction now. Now the overall reaction is, just a second, that's number 1. So I'll just copy paste these 2 reactions individually. This is number 2. So I've got my 2 reactions, and I'm just going to add them up. So add up the reactants, add up the products. So on the left side, it's 10. So just 10 plus, I think, 2i2. There's i2 plus i2, so 2i2 plus what else? There's 10 2 plus is there. And the products. What are your products? It's top equation, it's 10 2 plus. And then there is, I think, 4i minus 1. And then there is 10 4 plus. And this thing will get cancelled out because it's appearing on both sides. So this cancels out. So you can remove this from the equation 10 2 plus. It's appearing on both sides. And your final overall equation is going to look like, it's going to be this one. So it's going to be 10 plus 2i2 plus, and it gives off 4 minus 1 and 10 4 plus. So that's your overall reaction. So, but the thing happened in 2 steps. And you have to watch out for this. 10 going to 10 4 plus. Why did it take 2 steps? Because if you look at the 10 equation, you would notice that there is no direct equation where 10 goes to and gets oxidized to 10 4 plus. So you have to watch out for this. Like if 10 has, if a certain substance has multiple oxidation states, and there is no reaction where it's changing to a particular oxidation state in one go, then it would require 2-3 steps for it to happen. Tin was the one that was getting oxidized. It was losing electrons. Why was it losing electrons? Because iodine had a higher potential. So this got oxidized, then it got oxidized again. It lost another 2 electrons. So this is the overall reaction. So is this example clear? This one?
Yes, sir.
Okay, so but watch out for this, for specifically for substances that have multiple oxidation states, and you don't have an electrode reaction with where the substance, like I showed you an example, like for Fe that would not be an issue. Why? Because for Fe you have options. You don't have to like jump from one oxidation state to another one. Like Fe can turn to Fe2 plus. Fe2 plus can turn to Fe3 plus. But if you want Fe to turn directly to 3 plus, that's also an option. So over here, you won't have multiple, you won't have to do multiple steps, because you can do that in one step because they gave you an option to do that in one single step as well. For copper, again, you can do that in one single step as well. Copper turning into copper plus 1, copper plus 1 turning into copper 2 plus. But if you want copper to turn into copper 2 plus directly, there's an option available for that as well. So you have to watch out for, specifically for tin. It's going to be apply. It's going to get applied. I mean, this thing would be applied to manganese as well. You have to watch out for that as well, and for vanadium. So I'll do another one, which is going to be, and these are exam questions actually. These have appeared in exam papers. So I'll do another one, which is going to be even tougher. Not tougher, but it's just lengthier. It's time consuming. It's just a huge waste of time, basically. I mean, in your exams, I mean, if they give you a question, it's unfair, basically. But they have given these questions. Now, vanadium reacting with, I mean, this is a question that came for just 3 marks, but you would just realize that it requires a lot of working. One way you can save the time is, the reason it's taking too much time for me is that I have to copy the equations and I have to show you every time. In your case, the table would be in front of you. So most of the working, the equations would already be written. You just have to do the working or mark the equations on the table directly. So it would be less time consuming for you. But anyways, so we're trying to figure out what happens when vanadium reacts with Fe3 plus. So we'll just try and be quick. So I need equations for Fe3 plus. There are actually just two. So I'll actually copy all of them. So Fe3 plus, where's Fe3 plus? So these two. These are the two possible reactions that involve Fe3 plus. There's no other. So let's write that down. And I would need equations for vanadium. So hopefully there's only one. But you can see vanadium has too many equations. We just have vanadium at the moment, so I'm just going to copy this one. So let's make it quick. So who's the one, your reactants, remember your reactants are written right in front of you. So who's the one that's going to gain electrons? And who's the one that's going to lose electrons? So I think for losing electrons, it's going to be minus 1.2 volts. That's the lowest potential. So that's the lowest one. And it's vanadium. We do have vanadium with us. I mean, that's one of our reactants. So no issues there. Now, who's the one that's going to gain electrons? At the moment, it's going to be this one, the highest potential. That's the one that's going to gain electrons. So do we have Fe3 plus? We do have Fe3 plus. I mean, that's the only thing we have actually. We do have Fe3 plus over here. So we figured out the reaction. The first equation is of no use, and we can write down. The only thing is, I think we have to balance the equation, the number of electrons. So I need to multiply this by 2 so that the electrons get balanced. So my reactants are vanadium. And in the Fe equation, the reactant is 2Fe3 plus. And my product is in the first one, it's Fe2 plus, 2Fe2 plus. And the bottom one, it's V2 plus. So here's my overall reaction. TK, is this clear? That's reaction number 1. Is this clear?
Yes, sir.
So that's number 1. So now the question is, what is present in your container after the first reaction? So let's just make a beaker. What has happened? So after the first reaction, what do we have? We've got vanadium turning into V2 plus. So we've got V2 plus. Fe3 plus turning into Fe2 plus, right? And remember, it was excess Fe3 plus. So there would be leftover Fe3 plus. There is an excess of Fe3 plus. So I've got these 3 things. So I'm going to start again. Now I'm going to try and figure out what happens when these 3 things are present. Okay, so I've got my products and I've got the excess Fe3 plus. So I would need these 3 equations, I think, again. Just a second, I lost the board. Just wait for it to reload. So where are we? We are here. So I'll just first thing I'll just copy paste all these equations again, and I would need more equations as well. So these are some of the equations involving Fe3 plus. They involve Fe2 plus as well, and V2 plus as well. But I'll open the data booklet and I'll see if there are more such equations. So for V2 plus, you would notice that for V2 plus, there's another equation with V3 plus. So I'm going to copy all equations that involve V2 plus. So let's copy this one, minus 0.26. So here's another one. And for Fe2 plus, there is for Fe2 plus, there's another one with 2 electrons. So I'm going to add this one as well, because I now have Fe2 plus as well. So here are all my reactions involving my reactants. Fe3 plus, Fe3 plus, two options for Fe3 plus, Fe2 plus. There's an equation. Let me bring the equations, the Fe equations together. That should do it. So I've got all these reactions. Anywhere I see Fe2 plus, Fe3 plus, or V2 plus, two equations for V2 plus. And I'm going to do the same thing. The highest potential gains electrons. So which one is the highest potential? It's 0.77 volts. Acha, just a second. I've actually. It's just so our highest potential. Which one is it? 0.77. So that's the one that's going to gain electrons. And there's absolutely nothing wrong with it, because we do have our reactant Fe3 plus. Look at the beaker above. We do have Fe3 plus. So we figured out that has the highest tendency to actually gain electrons. Now we're going to figure out the lowest E naught. The lowest E naught at the moment is 1.20 volts. So that's the lowest, and that's the one that's going to lose electrons. But we have an issue, and that issue is there is no vanadium. Because if you look at the beaker, there is no vanadium. So I'm just going to cut that equation out. I'm not going to use this equation. So removing that, which one is my lowest E naught? The lowest E naught is minus 0.44. So that's my lowest E naught. That's the one that's supposed to lose electrons. But we don't have any Fe. I mean, look at the beaker. There is no iron. There's iron ions, but no iron. So we're going to get rid of this equation as well. So who's my lowest E naught now? I think it's minus 0.26. So this is the one that's going to lose electrons. Do we have vanadium 2 plus? If you look at the beaker, I think we do have vanadium 2 plus. So that is going to be my lowest E naught. So I've now basically finally able to figure out who gains electrons and who loses electrons. So I figured out this is the lowest and this one is the highest. And I'm going to add up the reactants and the products. The electrons are already balanced, so we can be quick with this. So who's my reactant? V2 plus. Who's my other reactant? That's Fe3 plus. And then I have my product, which is over here, it's V3 plus. And over there, it's the product is Fe2 plus. So we figured out this. So we figured out this second reaction. So this is reaction number 2. Okay, so is this clear that there's a second reaction? In the first reaction, the V got converted into V2 plus ions, and now the V2 plus, they've gotten converted into V3 plus. Ye clear? Is this clear? Nadine, is this clear? Zoha? Zahib, is this clear? Alicia, is
Yes,
this?
sir.
So now let's look at the beaker again. Okay, so let's have another look at the beaker. What's the situation now? Remember, we have added excess Fe3 plus, so that's still there. And what are your products now? It's V3 plus and Fe2 plus. So your beaker contains V3 plus and Fe2 plus. Remember, so these are your products that are formed, and the Fe3 plus was added in excess. So there's still some Fe3 plus left. So I'm going to try and figure out the reactions again. So I think most of these equations would be reused. I'll just copy them and I'll add new equations. So I'm trying to figure out the reaction once more. So Fe3 plus, Fe2 plus equations, that part is fine. Let me, okay, now it looks fine. I don't need, I think V2 plus is gone forever. So this equation needs to be deleted. It's because the beaker doesn't have any V2 plus ions. It's got V3 plus ions. So I'm going to keep this equation because it's got V3 plus. And I'm going to try and find other equations for V3 plus. So if you have a look, there's another equation for V3 plus. So I'll copy that one, which is 0.34 volts. So we're going to add that. Just a second. And I think that's about it. For V3 plus, we've got okay, so I think that's about it. For Fe3 plus, we have all these equations. For Fe2 plus, we have this equation and this equation. For V3 plus, I've got two reactions. Like in the data booklet, I've got for V3 plus over here, V3 plus over here. So I've copied both of these reactions. So I'm going to repeat the thing. Now a bit more quickly. Who gains electrons? The highest potential. So it's by default, it's the first one. This one. Why? Because this is the highest E naught. So that's by default my highest E naught. And yep, no issues there. And because I do have Fe3 plus, for excess Fe3 plus, that's still there. And who loses electrons? Now that's the lowest E naught. At the moment, it's I think minus 0.44. But we would have to get rid of this one because this is the one that's going to lose electrons, but the substance that's losing electrons is Fe, and we don't have any Fe with us. So we're gonna cut this equation out. Okay, I'm going to remove that. Who's the lowest E naught? It's this one. So that means V2 plus is the one that's going to get oxidized. But again, the issue is we don't have any V2 plus anymore. Look at the beaker, there's no V2 plus in it. So that is not there. So cut that out. Who's the lowest E naught now after that? It's minus 0.04. And I would have to get rid of this one as well because I mean it is the lowest, but again it's we need to have iron for that. And we don't have any Fe anymore. So we're going to get rid of this equation as well. So the only one that's left is the lowest E naught, that's 0.34. So that's my lowest. And will it lose electrons? It's going to lose electrons. Why? Because in my beaker, I do have B3 plus ions. I do have B3 plus ions. Look at the beaker, there's B3 plus ions. So I've figured out who gains electrons and who loses electrons. And all I have to do now is find out this third reaction. So this third reaction is going to be, the reactant over here is B3 plus H2O. So now where did this H2O come from? The assumption is that most reactions, they happen in aqueous solutions. So if they are happening in aqueous solutions, there's going to be water there. Okay, that's the, remember for water, water, if the assumption is the most reactions are happening in aqueous solution. So if water comes in one equation, even though it's not a reactant that is explicitly mentioned, it's fine. There's no problem with that. So I'll just make this up, B3 plus H2O, and the other reactant in the first one is Fe3 plus. So over here, the reactant is Fe3 plus, and the products. Now the product are, in the bottom equation, the product is VO2. And in the Fe equation, the product is Fe2 plus, and that's your third reaction, right? So we've had 3 reactions now. Now, since we are running out of time, the question is what the fourth equation, I'm going to see if there's going to be another reaction after this. So what does my beaker contain after this reaction? After this reaction, if you look at the equation, you've got VO2 plus 2H plus 1. All of these reactants, they've turned into these things. So I've got VO with a 2 plus charge. I've got H plus 1 as well now, and I've got Fe plus 2 as well. And I've got the unreacted excess Fe3 plus. Remember, Fe3 plus was added in excess, so it's still present. Now for this one, there's not, you can try and figure out, but you'll realize that there's not going to be any reaction for this one. This thing you can try and do on your own. And you'll realize that you won't find any equations, but very quickly, since we have a bit of time, I want to do this question in one go, so I'll just take 2-3 minutes more. For this one, I'll just do this on the data booklet instead of copying this. The reaction is going to stop at this point. So I've got VO2 plus. So where is VO2 plus? Let me mark those equations on the data booklet. So I've got these 2 equations for VO2 plus. There's VO2, VO with a 2 plus charge. There's VO with a 2 plus charge. I have what else did I have? I had those Fe equations. Those Fe equations were somewhere over here. Fe3 plus and Fe2 plus equations. So who gains electrons? Remember, this is 0. These are 0.77. So who gains electrons? The highest potential goes to probably which one? 1. This is the highest potential. So this is the one that's going to gain electrons, but you can't select that. You can't select that, and the reason is you don't have this thing. Your beaker contained VO with a 2 plus charge, not VO2 with a plus 1 charge. So you can't select this equation. So the highest potential by default, if you ignore that, would be the Fe1, which is 0.77, which is going to be this one. That's going to be your higher E naught. So you figure that one out. Now you're going to try and figure out who loses electrons. It can't be these ones, minus 0.44, minus 0.04, because it's then Fe that's going to lose electrons. You don't have Fe. Remember the beaker that you have, it's got no Fe in it. So the lowest one would then be vanadium 3. I mean, it's 0.34. But you don't have any vanadium 3 plus as well because your beaker doesn't have any vanadium 3 plus. So all your equations are getting eliminated. So the lowest one comes out to be this one. It's this one. So this is the one that's going to lose electrons. But the problem now is your highest E naught actually has a potential that's lower than the lowest E naught. Like if you look at the equation that you selected for the highest E naught, that was 0.77. When you were trying to figure out the equation for the lowest E naught, every equation got eliminated except for the last one. And that one had a voltage of 1 volts. So basically the whole thing collapses because when you were trying to figure out the lowest E naught, you didn't actually find a lowest E naught. The lowest E naught should have been lower than the higher E naught, but you didn't find any equation that was actually lower than this, because the lower one is the one that's going to lose electrons. And you ended up, by eliminating all the other equations, you ended up with this one. So, and that came out to be actually a high E naught. So that didn't make any sense. The low E naught has to be the low E naught, which in this case it's not. So is this point clear that you try and figure out the reaction, but you're not able to find the lowest E naught? Is this clear?
Yes, sir.
I mean, you can try doing this on your own. The problem would be that you'll be able to figure out the higher E naught, but you'll keep searching for the lowest E naught and you won't be able to find a lower E naught, because the lower E naught equation that would work would actually have a high E naught. So that would kind of not work. So the reaction basically stops over here. So let's and so these are the 3 reactions. There's one more step that needs to be done, and that is that add up all the reactions 1, 2, and 3, and you'll get an overall reaction. Okay, so let's. This is just one equation. We'll continue with this in the next class then. Okay. So, okay, everyone. Take care. Allah Hafiz.